Today we're going to have some fun with Solidworks and planar kinematics. So in Solidworks I've already created a base, an upper arm, a 10-inch long upper arm, and a forearm that is 6 inches long. I've just made these some thin style links here just so I can investigate the kinematics within Solidworks. I've also created another body which I've called Flat 1, and this is going to simulate the truck bed of our articulated forklift. I installed a second Flat 1 that is just a ground reference for the Flat 1 that is intended to move. When I first created this assembly, I brought the base part in first and I aligned its origin with the global origin. You see that here with this very first mate that makes the core origins coincident. Notice that it kind of self-suppresses itself. The next mate is a concentric mate that just aligns the revolute joints of the upper arm and the base. Then I have a coincident mate which sets the planar faces of the base and the upper arm. The next mate is a concentric mate for the second revolute between the upper arm and the forearm. Then I have a coincident mate between the faces. Now I've set some distance mates, which is just setting the flat bar with respect to the base. I have a coincident mate which sets the flat faces of the flat bars on the sides and on the front edge as well. Then I've just set a distance mate which sets where the flat bars are with respect to the base. And then I established the bottom reference flat bar with respect to the base. So that takes care of the main mates, if you will. These last three mates are really important here to establish how to do the motion analysis. Angle 1, angle 2, and distance 4 are important because we're going to use them to set our initial conditions for our motion analysis simulation. For example, angle 1 is currently set at 45 degrees, and that establishes the angle between link 1 and the horizontal ground. Angle 2 is currently set at minus 60 degrees, and that establishes the angle between link 1 and link 2. And then distance 4 is the mate that establishes the distance, the initial condition of the truck bed with respect to ground. So what we actually do inside the motion analysis is we actually suppress these mates from the get-go. So if I were to come up and suppress, for example, angle 1, see it's grayed out, at this point I can move. You can move the joint. Similarly, for angle 2, if I suppress that, I can move angle 2 and angle 1. And if I suppress distance 4, then the truck bed can go up and down, but all its other motions are constrained with the previous mates that remain active. So that's how you set up a motion analysis. So I'll just go back and unsuppress these. Okay. So I've already got a motion study already established. Notice that I have the motion analysis selected here as opposed to animation or basic motion. The motion analysis you actually get if you go to Tools and you go to Add-ins. You'll want, just like we had the SolidWorks simulation checked, you'll want to check SolidWorks Motion both here and here so that at startup you'll have it loaded again next time you start up. Okay, so here's my motion analysis selected. First thing I want to kind of show you guys is the icons over here. The first one is a motor. And we'll use a motor to drive. This is a SolidWorks motor. This isn't an actual motor. So this is meant to simulate the motion. Could be a linear, it could be a rotary motion that's desired. So that's what we'll use to drive our theta 1 and our theta 2. After the motor, we have the choice of a spring. And we'll use the spring to control the truck bed stiffness between the truck bed and the ground, the theoretical ground we have. The next thing is we have a damper. We probably won't use that in this example. You could establish a force that's acting on a component. We won't use that in this example either. An important one is SolidWorks contact. This simulates contact between selected components, and we will use this one because we're going to establish contact between the forearm and the truck bed. Gravity is also something we could use, but we're not going to use it in this study. Plot. We are going to do some plots. We're going to show some results in this example. And motion study properties, we'll come back to that one. Simulation setup. This is where we could additionally use stress analysis and whatnot that we'd used previously. So we won't use that in this example. Over here, we have the things that are happening as a function of time. The orientation here, for example, is established at time equals 0, and it's active the whole time. What you could do is change the view orientation by selecting some different views, and we're just going to use the front view for ours. Rotary motor. So I've already set up a rotary motor here for theta 1. So you can see here I've got theta 1 turning clockwise. Unfortunately, this SolidWorks is not very friendly with respect to SIGNs, and so I've kind of been forced into making it go clockwise there for my rotary motor for theta 1. Theta 2 is a rotary motor, or I'm sorry, the rotary motor 14 is for theta 2, and it also is established as clockwise. Solid body contact. I've got that turned on for the forearm and the truck bed. Linear spring 5, I have that turned on for the truck bed and the ground below. And these things are active throughout the duration of the experiment. Notice the experiment goes 0 to 5 seconds. Coming down here to the mates, here's where you can see that the angle 1, angle 2, and distance 4 are suppressed at time equals 0, thereby letting the two motors and the linear spring control those motions. The next thing I want to show you are these buttons in this area. This button calculates the simulation. This button replays the simulation from the beginning. This button plays the simulation. And this button here slides the simulation back or forward in time and lets you look at a particular snapshot. I find myself always resetting the slider to 0 in order to make any changes to a motor or a contact or a spring component. The next thing I want to show you is the individual components that we have here, starting with the rotary motor. Let's see what we have in that. Okay, the first thing is the motor location. And there's actually a couple things selected here for motor 1. So if I zoom in, I'd be able to see that I've chosen actually the two cylindric pieces of the rotary joint there, the revolute. And here I've picked a direction, which is clockwise, and I've picked a component to move relative to, so that would be the base. So that sets up the motor, the first motor. To specify the motion, we have a number of options. I could do constant speed, which is the first thing I showed you. I could say, okay, 1 RPM clockwise. I could set it up to be oscillating, whatnot. What I did is actually selected expression. And when I did that, I selected data points and actually imported the data from what I generated in Excel. So I'll come back to that. I've already got it set up for this scenario, but I'll come back to that and show you how I did that. So actually, after I do that, it says data points. Repeat that for the second motor, and then the second motor, it's just that you're doing the forearm with respect to the upper arm. So that's all that is. Solid body contact is important. Here I'm looking at the forearm and what would be the truck bed for this scenario here. And Solidworks likes to, by default, say everything's acrylic. Of course, we'd want to go in there and actually change what this would be. Or you could deselect the material and actually go in and control what the coefficients of friction are, the dynamic and static versions of those, and then you can also control what the impact properties are. So that's pretty cool. So that's contact. And then linear spring, what I do there is I've got a spring that would simulate my truck bed stiffness, and I've actually controlled the faces that would displace relative to one another. So I picked the bottom faces of these devices, the bed and the ground, the simulated ground, and I picked a spring constant 10 pound force per inch just for this example, and a free length of 5 inches, which is where they have been set with my simulated or with my initial condition mate. So that's kind of set up the simulation with the exception of telling the motors what to do. That's set everything up, everything that we need. Down in the results sections, I've already set up some plots. I've set up motor torque plots. I've set up the Y velocity. I've set up the spring force. I've set up the Y displacement, X displacement of the end point with respect to the shoulder. And I've set up the motor angular velocities so that I could see what they are. So as I say, the simulation's pretty much set up except for putting in the data for the two motors. Okay, now I'd like to go through and show you how I did my theoretical model. I used Excel for this simulation. You could use MATLAB or quite frankly, whatever you wanted to use. It's good to have a way to plot, though. That's one thing you want. In my example, I set up the lengths here for my upper arm, which was 10 inches. I set up the forearm as 6 inches, and then I did my initial angles, theta 1 initial and theta 2 initial. And notice I've used my convention as far as sine, so that was an elbow down, so minus 60 for my theta 2. And then I set up, actually through calculations, set up what my shoulder to forearm endpoint X is. And you can see my raw calculations here, the equation, and the same for Y. So I've set up the X naught and Y naught. I've also set up the Y acceleration. What I'm going to do is I'm going to take the end of the forearm, that point, and keep X constant, and then accelerate Y and drop Y from the original position of 5.5 roughly inches, and drop it down so that my Y final is actually minus 2.1. And based on how I've set everything up, what that would do is that would actually displace the spring 2.5 inches. So this Y displacement will go from 5.5 to roughly minus 2.1 down. The acceleration is set up at 4 inches per second squared. The slewing speed will be, the highest speed reached will be 2 inches per second. The time to accelerate, I have that calculated based on the acceleration of Y and the velocity of Y. And then my time to slew is also based on the parameters here that I've set, so that's calculated. The truck bed stiffness I've set up as 10 pound-force per inch, just in the simulation. And the Y position where the spring will start to displace, I've set that up as the 0.4. So that 0.4 positive going to minus 2.1 for Y will displace the spring, the 2.5 inches. So theoretically I should get 25 pound force for my spring. So these parameters here set up what I need for theoretical. And notice that I have renamed some of these cells based on some variable, and it's kind of hard to use L1 in an Excel file, so because L1 would mean a column L in row 1, so instead of using that, I prepend an MWG on the L1, and same for L2, and my theta 1 original, my theta 2 original, and then my X naught, I've just called it X naught. My Y naught is Y naught, AY, etc. So I have these things kind of set up so that in my equations I can just refer to those variables. Over here I've got the KT and the Y spring. So that kind of sets me up so that I can come down here and theoretically fill everything out, have my functions as have things as functions of time. So starting here with time, I started at time 0, and for my simulation here, just going for 5 seconds, I did that in 20 millisecond intervals. So if you see my equation, each cell is the previous cell plus 20 milliseconds. So I did that all the way down to 5 seconds. And you would need to change it to however long you run your simulation. Then I did as a function of time, I did the y position. So the y starts at the 5.518 inch, etc., and then it diminishes as I'm dropping down based on the trapezoidal velocity profile that I put on it. So you can see the function here. Okay. Then theta 2. So I'm just going through the kinematics here. There's some supporting documents for this that you could refer to. For the kinematics, I start theoretically figuring out what the theta 2 should be, and this column is the theta 2 in degrees, and this column should agree with my notation for what theta 2 is, and so I'm using a minus a cosine, and it's just the cosine law here to get theta 2s. So I put theta 2 first because it's easier to get. And then over here, I've got my theta 1, and it's similar to the 3r, how you would solve it. And I've got the equivalent function here based on a tan 2 and a cosine. So I have that. So as a function of time, so you notice that time's handled, for example, with whatever A18 is. Actually, I dial up based on the y. So the y is looking at what A18 is and setting the y position accordingly. And then the theta 2 actually refers to the current y location, which is B18. So where you see B18, that's the current y. Same thing here for theta 1, where you see the B18, that's the current y that it's referring to. And then everything else would be your constants. Here's an important one. Remember that Solidworks is it's expecting you to start at 0 from the initial condition. So what I have to do there is I have to take my C18 and subtract off the original theta 2, and then Solidworks is going clockwise instead of my normal counterclockwise for positive. So I have to actually put a negative sign there. So this is what theta 2 is doing here. This is actually the column that we'll send to Solidworks. Same thing for theta 1 for Solidworks. I need to subtract off the original location and then negate it because its positive is defined as clockwise. And then what I did is put in what my y dot is doing. My y dot is a time rate of change of y, so this is the trapezoidal profile, and this is theoretically what it should do. Then I did a reverse velocity analysis to get what my theta 1 dot and theta 2 dot are doing, and then I converted these to degrees per second. So again, this is depending on the Jacobian. There's some supporting documents for this. The next thing I did was calculate what the spring force should be, and if my y value is above that y spring position, I say my spring force is 0. Otherwise, I say it's minus the spring constant times the y, the difference in the current y and the y spring value. So that sets my spring force. And of course, near the end is where I start to come into spring force, and I should end up at 25, as I said. So that's good. The last thing I do is I predict what the torque 1 and torque 2 should be. Those are the torques of the motors. And of course, that's dependent on what the spring force is. There's some supporting documents to calculate how to show you how to calculate the torques. It depends again on the Jacobian, the same Jacobian that you used for theta 1 dot. So basically, I have the torque 1s and torque 2 coming into play once the spring force becomes active. Okay, so theoretically, I'm kind of all set up here for the most part. One thing I can show you is I created some graphs that have the y displacement as a function of time, the predicted y displacement or desired y displacement, the trapezoidal velocity profile for y. The theta 1 dot, this is really calculating that one column with respect to time. So for example, if I look at what theta 1 dot is, if I come in here and say, okay, what's my data for this plot? And I'll just say edit it for now so you can see what it is. So theta 1 dot is looking at the theoretical sheet. The A column is my X, and the theoretical sheet, the H column is my Y for this graph. Let's go back and take a look at what the H column is. Yeah, so the H column is my theta 1 dot, so that's how that works. I repeated that for theta 2, for torque 2, and then of course the spring force. So I'm kind of set up for the most part. The only thing I haven't shown you how to do yet is how to generate a comma-separated file for downloading generating your theta 1 Solidworks and your theta 2 Solidworks. So what you can do is go up to File, and you say New, Create, and then what you can do is go back to, say, grab this column, grab that column. Let's say we're going to do theta 1 first. So we do that column and that column. So you copy those, and then you go to your new file, and you paste them there. Paste values, so do that. Now I want to get rid of all this upper stuff here so that I only have the two columns of the time and the theta 1. That's what I want. So I delete that. So I've got the columns that I want. Time is A, and B is my theta 1. And then I go File, Save As, and here I want to save that as a comma delimited comma separated variable file. And I'd already had one defined up here, theta 1 Solidworks CSV. Then you would save, and it'll complain to you, are you sure you want to save this? Because basically what you're saving is not an Excel file, you're actually saving a text file, and you can actually look at this text file say with something you can edit a text file with, like I use Crimson. And so you can see it is just a very simple text file that you can generate easily in MATLAB or any program. So it's just a text file, and then it ends at 5 and 28 degrees. So that's what it looks like. You repeat that for your theta 2. Okay, so we're all good to go there. I'm not going to save them because I've already done it. Okay, so that's how you set it up. Okay, back on the SolidWorks side, I'm ready to download what I want my motors to do. So I select Rotary Motor, the first Rotary Motor, and then I go into the data points and edit that. And I'd already done it, but I'll tell you what, I'll delete that row right there. So this is what you would see. And then you just simply import your data. That was for theta 1, that was the first motor. So I'll select T1 SW for that that I had just exported previously. So I say OK, and it brings it right in. So it's just that easy. You've got some things you can toy with here. I'm going to leave it as a cubic spline, which says, hey, what's happening between the points. That's fine for now. So I say OK, and I say check that. And then I would repeat that for the rotary motor, and by gosh, I'm definitely ready to go now. I reset, and basically what I do now is I calculate. And that's it. I just did it. You saw what the end effector did. The point did go, it kept a constant X, and it did go down, and it buried into the truck bed as we kind of expected. What I can do is I can come down here to the results, and I can plot them. Let's look at the plot for what X and Y did. So I go to that plot, and I can say show it. And oh my gosh, it's I already see a problem here. It's the Y is showing it's going from -6 to +2 something. So let me go tweak that a little bit, see what the heck's going on. Let's see, edit feature there. Y component. I think here that these things are backwards. So what if I were to, let me delete the link one location. I'll delete that one and then I'll add it back. Nope, that didn't do it. Let me delete the first one and add back base. Okay, so I effectively swapped those. Let's see if that fixes this. So now I come and show that plot. Yeah, so now it's going from the 5 whatever down to the -2 whatever. It looks like the X in red has been pretty solid in its location. So the first thing I'm going to do here is I'm going to click over in this area and do a right mouse, export CSV. So when I export CSV, I'm not going to use its suggested file name. I'm going to put x-y-sw out. So I know what that is. Save. Got that taken care of. So that's that one. And then I could do the same for my y velocity. Let me show that plot. Hey, there's that trapezoidal profile, so that's looking familiar. I'll export that. So I'm going to call that y vel out. Well, let me call it y vel sw out. Save. We got that. Let's look at the angular velocities here. Show plot. So there's my theta 1 dot, theta 2 dot, and degrees per second. So I'm going to take and export that. I'm going to call that T1, T2, vel SW out. So I know what it is. I've got that. Then I'm going to look at the reaction force. Now that's my spring. I'm going to view that. Show plot. So hey, it's looking familiar. 0 coming up. Bloop, bloop, bloop. So looking at 23. That looks strange. 1 and 25 there. I go over this area. Export CSV. Spring SW out. So I've got the output there. Kill that. Let's see what I suspect something's going on here. Oh yeah, the nose kind of embedded there. We again violated some laws of physics here and embedded the nose into the truck bed. Okay, so we could investigate that later, but the simulation is not quite right. So I've done everything except for motor torque. So let's see what the motor torques would be. Show plot. So here you can kind of see there's a bump there from the impact, and then it tracks up. So let's save that. Export CSV. So I'm going to say torque 1, 2, SW out. So kind of captured everything and sent it to file. Okay, so that's what the simulation did, and of course I can set it back, and then now I can play it. So you can see what it's done. Nice. Okay, the next thing I want to do is get back into the Excel side, and I want to import the results of the Solidworks simulation. I want to import that into my Excel and compare it to what I expected. So if I go to my directory and let's pull up, for example, Y velocity Solidworks out. I'll open that in Excel, and what I'll do actually is come down here to the bottom and go right mouse, move or copy, and actually want to copy it over to the book, the other book that I have, and move it to the end, create a copy. So I should have that when I go to my other book. Book 4 is the book I'm working out of theoretically on the theoretical side. So it took the Solidworks output and appended it as its own sheet. Okay, and of course we've got copies here, so we're in good shape. Now I want to go ahead and delete the first two rows. Delete. And the reason I do that is because I want to add this, when I have conveniently add the time and the y velocity over to this graph, the y velocity graph. So how I do that is I come over here, do a right mouse, and I say select data. And what I'll do here is, of course, I'll keep the y dot there, but I actually want to add another plot to it. And here's how I do it. So for series name, I'll call it y dot SW. Okay, and then for my x values, I'll select range. So I'll come over here to what I just added, that sheet I just added, and I'll just select A. So I'm good there. Then I'll come down here and do the same for my y velocity, my y dot. Select B, and it should be good. Let's see what happens. Okay, so you can see the results of what we desired was in blue. It went down to the -2, and the red's coming up a little bit short, so that's interesting. But generally speaking, I got the trapezoid that I wanted. So that's looking half decent. Then I can go and add some more. Let me close that CSV. All right, and let me go add some more. Let's see what our XY SW out is doing. So I'll do that. I'll come down here and I'll go move or copy. Put it over in book 4, my theoretical thingy. Move to end, create copy. So I can now close that one. Okay, so here again, I'll just delete the first two. So it's actually the Y and the X position, so I can delete those two so I can plot them easier. You can see the last column is the X. It's been solid. The last column is X and it's solid. Looks like -12. Well, looks like it was confused on which way to measure that, but 12.866. Let's see what we desired theoretically. Theoretical side. My X naught, yeah, it's right on the money. So it looks like we're good there. Now let's plot the Y. Go back to my Y displacement. Want to add the Y. Select data. Add. And I want to add, so this will be YSW as a function of time. I'm going to select range, come over here, and for time select that one, the A, and then for my value I'm going to pick the B column. Should be good. Okay. And they're right on top of each other. You can't tell the difference. So that's looking solid. Okay. Next one is my theta1 dot, theta2 dot. So let's go in here and bring up T1, T2, velocity, SW out. So I'll open that one and come down here and say move or copy. I'm going to put it into book 4. I'm going to move it to the end, create copy, OK. Close that. Cancel. Wait a minute now. Oh yeah, I'm good there. I wanted to close this. I don't want all these things open. Alright, so I'm good there. So I've got my theta1 and theta2 dots. That's what these are. Don't want the first two rows there. Delete that so it's easier to add my stuff in here. Graph, come over here, select data, add. Okay, and then I'm going to say this is my T1 dot dash SW. I'm going to say my X values are down here. That guy, there's my X value for the plot this time. My Y value is going to be the B column. So it should be good. That's theta 1. Okay. See there's virtually, the red has virtually covered the blue, so we're in good shape there. Okay, so that took care of theta 1 dot. I repeated it already here, theta 2 dot. You can see that bringing in the SolidWorks just lies right over the desired, so we're in good shape there. The next one I did was the spring force. And the actual spring force, remember, we didn't displace the spring as much because the nose of my end effector dug into the truck bed. So that's something that we need to resolve. But anyway, it's pretty close. 23 pounds. Came up a little short there. And the torques kind of reflect that. The anticipated torque was higher than what the actual torque was. Remember, I had that little bump due to the impact, but generally it's following what we thought it would. Same for torque 2, a little bit of a bump there, and generally followed what we thought it would. So we're in kind of good shape here. Generally, our theoretical model was for the large part verified by SolidWorks. There are a number of things we could do to improve the results. If we're going back to the SolidWorks side, I can take a look at the motion study properties. There's some things I can do here. I can play with the frames per second. I can look at the accuracy values. So I've got some advanced options. So that's one thing I could do to improve the results. Look at more frames. Another thing, another critical area here would be the solid body contact. Could go around and play with those things here. Remember, I had left these with the acrylic materials here. So there's some areas. There are 2 areas right there that I could play with in order to get better results, or results I would expect to get. Not getting the nose to embed into the truck bed would be the one thing. So for a more complicated project, like maybe the articulated forklift, we might want to turn on gravity. We might want to turn on solid body contact between the forks or our robot and the object we're picking up. And then we would want to turn on solid body contact between the object we're picking up and the truck bed. And then we may want to look at a number of segments that we put together in order to have calculate our thetas. So going and looking at what we might have in our equivalent Excel file, we would have columns for X, Y, and gamma maybe as a function of time, and we would have T1, theta 1, theta 2, theta 3 actually. We would have complementary columns for SolidWorks, T1 SW, T2 SW, T3 SW, and then we would predict our X dot, Y dot, gamma dot. We would predict our theta 1 dot, theta 2 dot, theta 3 dot, and then we would predict our loads as a function of time that the forks would see, and how those loads would reflect back onto the joints, individual joints, and provide torque 1, torque 2, torque 3. So the scenario for the forklift project would be where we're picking up an object, so we should see torques during that period, and then we're carrying that object and putting it on the truck bed, and we would start to see that load on the joints diminish as the spring truck bed spring starts to accept the load that we're putting on the back of the truck. And then at the end, we should see 0 torque loads, and then that way when we pull out our forks after that, the object will stay on the truck bed. So that's kind of where we would go in a more complicated project. But the rudiments of that project are kind of here. So in summary, what we've shown you here is how to do a SolidWorks motion analysis study. We've set up the physics where we've got solid body contact. We've got some forces that could act on the end effector due to this displacement of a spring. And then we've gone in and actually told the simulation how to move the individual motors. We've got the how to move the individual motors in such a way that we expect the coordinated motion of the endpoint so that it would actually drop. So SolidWorks demonstrated that, yeah, if we give it those data as a function of time that we've calculated, yes, the end effector does what we expect. SolidWorks is showing us that we're good there. And then it also gives us feedback what the torques are going to be on the individual motors, what the forces that are interacting are. So it's given us that feedback, and then that feedback we actually compared to what we expected. And then we were able to say, hey, this is a good simulation. It agrees with what we think it should. So that makes us much better engineers. And I hope you've enjoyed our discussion for the day.